So this lecture, we're going to continue with where we ended last time. So last lecture we discussed other aspects of premixed flame phenomena, specifically the flammability limits and some extinction issues such as flame quenching. And we talked about the fact that flame quenching really is the other side of ignition processes. So on the one hand, for premixed flames, once you are able to understand what the processes are that drive the extinction process, then it's relatively easy to start to think about the issues that drive the ignition processes. And so this lecture will focus on ignition issues. We'll certainly begin with sort of general ideas in ignition and hope to cover topics through liquid ignition and solid ignition. We'll see how far we're able to get on that. To motivate some of this, I want to talk about an issue that you've heard of and oftentimes becomes the in some sense diagnosis or the cause of last resort when people are doing forensic reconstruction for fires, and that's the idea of spontaneous ignition. And so spontaneous ignition is probably not what you think about when we describe it mathematically, but it really is just a trade-off between exothermic heat release and the insulating property of the fuel bed. So the first thing I'm going to do is I'm going to point you towards a YouTube video. So we're going to switch to our main monitor here, our main PC, and when you do, so look at YouTube and look at super glue plus cotton wool. So if you have a, don't try this at home, but you'll see that there is an aspect of even some simple reactions like this that could cause spontaneous ignition and combustion. So let's play through it, and I'll walk you through what they're looking at. Okay, so cap to put the cotton swabs, cotton balls in, and this person's going to saturate it with super glue, and super glue is made of cyano and sort of a methyl ester, and so it's a monomer that is going to polymerize, but in the polymerization process it's exothermic, and the cellulose in the cotton swab is what is in some sense catalyzing and helping this this polymerization process occur. So there's an exothermic reaction that's taking place between the superglue and the cellulose, and the insulating properties of the cellulose keeps that heat in to the point that if the external temperatures are high enough, so if it's warm enough on the outside, you'll actually get a flaming reaction. Now, not in all cases will this happen. So my students have looked at this in the lab, just playing around with these, and you have to configure it properly for it to occur. So the simplest way is you put a hot plate underneath, so that certainly helps. You put a lot more cotton swabs around the part that is primarily exothermic so that you keep the heat in. So this is it's a hard to reproduce condition, but it gives you an idea that when you have a porous fuel bed, and porous in the sense that you can have oxygen transport into it, that coupled with some sort of exothermic reaction will cause this spontaneous ignition. So what we want to do is we want to talk about what the factors are and how to analyze systems like that. So this lecture will talk about autoignition, which is different from what we just saw, spontaneous ignition. Okay, we're getting there. Spontaneous ignition, evaporation, and okay, that, and liquid ignition and solid ignition. So just give me a second here as we get our pens all set up. Now we need to choose our pen color. There we go. All right, so we saw this example of the YouTube video. In this porous cotton ball matrix. All right, and I'm going to just make some comments here about, again, the nature of ignition. So for ignition processes to take place, the thing that we're looking for in these ignition processes and ignition phenomena is that the energy addition must be greater than energy losses. So this seems sort of obvious. And any excess between the addition and the losses should be able to raise the temperature of the system to a point where this thermal runaway can occur. And we'll see lots of different examples of that. So if you look for ignition or ignition classification of hydrocarbon systems in reference books or online, one of the things that you'll find quickly is that there is American Society of Testing Materials standard ASTM E659, and what that test does is it classifies liquids, hydrocarbon systems, others, in terms of something called an autoignition temperature. I'm not a big fan of the use of the autoignition temperature for practical problems because I think that it gives the wrong message to people. So oftentimes when you look at depositions, for example, or testimony, or people who are perhaps less technical talking about issues of ignition, a lot of times they'll cite the autoignition temperature of a particular liquid or a particular fuel relative to another as the reason why they think that a particular accident occurred. I would argue that the autoignition temperature is more a measure of the low temperature chemical decomposition of the system as compared to an indication of the ability of that system to ignite under, oftentimes very different conditions. So just to talk about what the test actually entails, you can imagine that a flask where there is some sort of heater control. So imagine that we have this vessel where we might be able to resistively heat it and modify the temperature of the wall, and by definition really the temperature of the mixture inside. We're able to monitor, for example, we can imagine that this is even closed off and we can measure sort of pressure of the system and otherwise, and we can figure out if this system has an ignition process. And this ignition process is not necessarily a flame because this is homogeneous and it's heated, so there are no gradients inside. There are presumably no temperature gradients. It's there are obviously temperature fluctuations, but there's nothing local per se that would cause any part of the system to run away any faster than any other. So what the standard requires is a determination of the time to ignition. And so if one were to plot the time to ignition as a function of, as an example, this wall temperature, this control temperature, you would see that at very high wall temperatures, it ignites readily, and as you decrease the temperature, it takes a longer and longer time to ignite. And so when a 10-minute time delay is proposed or looked at, that's the asymptotic value, so we're getting longer and longer. The temperature at which that occurs is considered to be representative of this autoignition temperature. And as I said, it's perhaps more an indication of the thermal stability and oftentimes the relatively low temperature thermal stability of a fuel as compared to really something that specifies the ignition hazard posed by that particular fuel. We'll see shortly why this 10-minute delay time might not make much sense. If you think about it, again, whether you're talking about a spark ignition or you're talking about a ignition over a hot surface, typically the residence time for a fuel-air mixture in contact with anything reasonably hot is of such short time duration that there are many other factors that are controlling the evolution and the dynamics of the system as compared to what is required in this, again, relatively long residence time measure like the autoignition temperature. So when we look at autoignition temperatures for typical, I'd say perhaps fuels and hydrocarbon systems in general, carbon monoxide, hydrogen obviously are not hydrocarbons there. But when you look at it for a range of, again, typical fuel species, we see that we're talking about things that start all the way at about 206 degrees Celsius, which is not particularly hot, all the way to 600 C for methane. And so methane is known to have sort of odd decomposition characteristics, but really in terms of overall ignition characteristics, in terms of flame propagation, etc., methane is not that different from propane if you look at it globally. So this again reinforces the point that this is these temperatures in particular, as we look at these some of these relatively low values, are more indicative of the fuel stability. Now, one of the things that autoignition temperatures might be important for, from a practical perspective, is some of the processes that happen in spark-ignited engines or in diesel engines. So the propensity to knock in fact in an engine system, so engine knock, is an autoignition process. It's this homogeneous ignition process that, again, occurs at relatively low temperatures. So that ASTM standard is very useful for understanding that aspect of the stability of the fuel-air mixture at temperatures that are, again, comparable to what you might see in cylinder issues, but less important from a fire safety perspective. Okay. That said, the basic issues that are controlling autoignition or any other ignition process are all generally the same from a theoretical perspective. And so it's a useful way of formulating and understanding the theoretical issues in ignition. So an abstraction of what this ASTM standard discusses is shown in this schematic, where we have a tank that's filled with a premixed charge and where the walls are maintained at some TW. Well, we understand that the heat losses to that system look like H, where H is the heat transfer coefficient. So this is Newton's law of cooling. So I'll put that here. H is our heat transfer coefficient. We have the heat losses are proportional to temperature difference. So our delta T is the difference between the wall temperature and the gas temperature difference. A here is our surface area. I might put it A sub S. And our generation is proportional to the volume of the system. So this is, we have a volume here. And this model is called an Arrhenius reaction model. So the Arrhenius reaction model says that there's an energy threshold, and in that Arrhenius reaction model we have several parameters. E in that model is called the activation energy. So that's the energy threshold that's required for the gases or the molecules inside such that we're able to get reactions. R is just the universal gas constant. And you know what? It's probably worth just a small departure to talk about this Arrhenius reaction model. All right, so I know that many of you are going to be sick and tired of this diagram, but I'm going to do it one more time. No, I'm going to do it many more times. But let's, we're going to end the show. We're going to keep our annotations. And what we're going to do is we're going to insert, well, let me see something here. Yeah, we're going to insert right here another slide. And then we're going to go back to our slideshow and go back to our pen. Go back to. Okay, so let's talk about this Arrhenius reaction model. So, sort of a simple model for reaction. So we have, imagine we have, again, species A and species B. So we, in fact, we'll, again, W and B, and W and B form some species C. So we're going to look at the system that is composed of these black and white molecules, and just by virtue of the fact that they're at some temperature, they have random molecular motion. So they're all moving and translating by virtue of the fact that they're at some temperature. Now, we have a reaction mechanism that, I think I call them W and B, right? W plus B will go to species, let's call it A, or we'll call it P for product. Okay, so this is in fact, and I'm going to modify it even slightly more. This is a better description. So this is our chemical reaction, sort of global reaction descriptor. And I think we've talked about this before, where these coefficients, the nu sub I, are oftentimes called our stoichiometric coefficients. Okay. Now, in fundamental reactions, the idea is that this law of mass action must hold, and that we really have simple collisions between the molecules. If we wanted to talk about the rate at which, for example, we were to deplete species B, then we could write an equation for that rate of depletion, either in terms of the density, concentration, mass fraction, etc., of species B. And so we might say, for example, d rho B dt is equal to, and then here's where our Arrhenius law would hold. And so we imagine that that relationship should depend in some way on the relative concentrations of species B and the relative concentration of species W. And this has to be normalized for, so I'm going to just even put a normalization in here, times a rate constant, a rate coefficient, times this Arrhenius type relationship. And so let's see if we can make sense out of why this has to be true. So there should be a dependence on the relative amounts of B and W, and there's always a dependence on the temperature. And let's follow this through. So one way of describing this is by considering the fact that if we were to look at some scattering volume, so imagine that we enclose some path around all the molecules where there's a collision area that has to encompass the diameter that is associated with a collision between the B and the W molecules, then we can ask ourselves, what's the characteristic velocity that allows this to occur? So there's some volume, there's some swept volume that occurs associated with this process. So the swept volume and some delta T looks like this cross-sectional area where this is the characteristic diameter or radius of this molecular collision times the characteristic velocity, and this is a characteristic molecular velocity times this delta T. So if this is the swept volume, we can describe the number of collisions that are going to occur in there by the, say, number concentration of type W molecules. So I'm going to use NW as this number concentration of type W times pi, again, sigma c squared, UCH delta T. This is the number of collisions with one type B. So sort of this is very much hand waving because it's more complicated, but with all type B, you would imagine then it would be an NB NW pi sigma c squared UCH delta T. So approximately the number of collisions with all B has a rate which this UCH looks like T to the 1/2. So sort of this is representative of our rho B, rho W. So this represents our densities there. But we know that not all the collisions, so we, even at room temperature, we have collisions occurring between, say, methane and oxygen, but we're not getting a significant rate of heat release or modification in the number of species that are changed. And so as we look at now the, so this is where I said you're going to be mad at me. So as we look at the enthalpies of the reactants versus the enthalpy of the products, something strikes us, and this is the fact. So this is the diagram that we've always drawn when we talked about, for example, the enthalpy system between the reactant system and the product system. This is a global description of what's going on. If we're talking about the energy of the system from a molecular perspective, we might say, for example, that the molecular energy between the products, and this is going to be in terms of the reaction progress. So the energy of the system would look something like this. So we have our reactant energy, and then we go through something called, again, and to go between our reactants and our products. So over here is the energy of our products, over here is the energy of our reactants. But look at this, you have to go over a higher energy, you have to go to higher energy before you get this difference. So the thermodynamic energy difference, this is right here. This thermodynamic energy difference is the thing that we're observing globally. I'll write it like this. Over here, it's the energy difference between the reactant system and the product system at the same temperature. So, you know, you're saying, well, you know, gee, this thing is, you know, the reactants are at higher energy. So what's the problem? Well, in some sense, you have to break the bonds even in the reactants. You have to set up a new system before you can go to this lower energy state. And so the energy that's required to overcome this threshold is this activation energy. This is the E that we're talking about here. Another way of thinking about it is in terms of a Boltzmann distribution, where we look at, for example, the distribution of energy of the molecules in the system, and we ask ourselves what proportion of the overall distribution of the molecules in this system, when they collide, have an energy that exceeds this critical energy. And so that proportion is where we're getting our exponential of minus E on RT. So this is the thing. It's the Boltzmann distribution. It's the Boltzmann distribution description of the fraction of molecules with appropriate energy to overcome this energy barrier and to allow this ignition process to occur that is driving this Arrhenius model description or Arrhenius model form for the reactions. So to summarize, what we want to understand from that is for a reaction to take place, you need both, you know, type A particle and type B particle, or black and white, or methane and oxygen. You need those obviously to be present, but then you also have to have an appropriate temperature to cause the energy to be sufficient to cause this reaction to take place. Okay, and so this is what we have been describing. So in terms of this ASTM model, we can imagine that our reaction rate is very strongly dependent on temperature. This is our exponential of minus E on RT. This is a very strong temperature dependence, just runs away. Now, these lines here are the heat loss lines. And so what we're asking really is, and I'll do it here, if our reaction, so here's a case, at low temperature, our reaction rate, our total amount of energy release is larger than our heat losses, so the system moves to this stable state. So at low temperature, you start to heat up the system because of internal reactions, and the temperature of the system has to shift to a point where the reaction rate balances the heat losses. On the other hand, if we start off at a temperature over here, it shifts down such that it moves towards, that's interesting, it moves towards the this stable node where again reactions balance heat losses. If we were to start higher, then all of a sudden there's a thermal runaway because it's always going to be moving. The reactions are always larger than the heat losses. As we change the temperature, there's a critical temperature where it's tangent, and so that tangent condition is associated with this autoignition temperature. And the typical question that arises, and it's a theoretical question more than anything else, is that really this heat loss, the vessel was at T1, but this tangent condition is at Tc. So, oftentimes the question is, what's the difference between the gas temperature, the reactant temperature, and the wall temperature? So as far as a correction is concerned, to more appropriately identify what this autoignition temperature is. So you can assume that this AIT is the tangent condition between the heat losses, which again are H delta T, and this exponential of minus E on RT. Okay, as I said, it's a more theoretical question. Here is what the type of instrumentation people will use for determining the autoignition temperature. Okay, now what we said is that autoignition is a balance between heat generation and heat losses, and that this also helps us understand spontaneous ignition, which is more representative of what we saw in this superglue cotton ball reaction. Okay, so when fire investigators look at different types of fire accidents to determine the cause and the origin of the fire, one of the things that in the back of their minds they're thinking of is, could this have possibly been a spontaneous ignition fire? And as I mentioned at the beginning of this lecture, oftentimes that is the causation, the determination after all other results have been excluded for hopefully good reasons. And certainly there are cases where it is obvious it is a spontaneous ignition. So a typical scenario where you might have a spontaneous ignition is where some structure is in the final stages of a renovation. The painters are there, and they've been working on, say, a Friday, and there's a long delay before they need to come back, and they clean up their painting tools and they clean up the structure using rags and some sort of paint thinner or oil. And generally what happens is that these rags then obviously get saturated and soaked with the oil, and a lot of times these things are bunched together, heaped together into some garbage can or into some corner in the structure, and we get reactions that are very similar to the types of reactions and processes that happened in that superglue cotton ball problem. And so, as you know, oxidation continues to happen. So oxidation is happening all the time. We are oxidizing, and there are oxidation processes within our chemical system. Many organic materials are oxidizing around us. The issue is the rate at which they're oxidizing is very slow, and they're oxidizing in such a way that even if this oxidation process is exothermic, again, where there's heat generation, it's balanced by the heat losses from it. And so the temperature of the system is steady. But what happens, of course, is when you start to imagine a relatively large amount of an oxidizing system, where that system is more and more isolated thermally from the environment, then with this high resistance to heat loss, the oxidation process is generating heat, is incapable of releasing that heat to the environment, increases the local temperature within the system, which accelerates the oxidation rate, which then in a feedback process causes this thermal runaway. Okay? So, with all ignition processes, the heat generated is greater than the heat loss, and that's what causes this ignition process to occur. The way to characterize it is in terms of heat transfer terms and heat transfer concepts. One of the things that we'll see is that the characteristic length of the fuel bed, the heat transfer parameters associated with losses to the environment, and the inherent kinetics of that oxidation process are the things that are going to drive the likelihood, propensity to go into thermal runaway. So, if we look at a really simple example, one that's analytically tractable, we get a lot of the features of what is actually occurring. So, imagine that we have a porous matrix. That's what we're showing here. So it could be oily rags in a pile, coal dust, cellulosic materials. It doesn't really matter. As I said, there's slow oxidation of this material that results in a small volumetric heat release rate. So the triple prime, this Q triple prime, has units of watts per meter cubed. And as we know, the heat release rate is put into this Arrhenius form, where this delta Hc is something that we've seen before. The delta Hc is our enthalpy of combustion. So it's the amount of heat that's generated as we consume some mass of the reactant. We've talked about the exponential form already. Now, the challenging combustion problems mathematically is the nonlinearity of this term. And so computationally, it's not an issue, obviously. I mean, it's a stiff system, but from an integration perspective, it's something that is we can do computationally. Analytically, of course, it's a much more challenging problem, but even then there are approximations. But just, again, to get insight into this problem, we're going to look at a simpler problem by just assuming that we have a very simple temperature dependence for this energy release rate. So we're going to assume that the energy release rate is equal to a constant plus a proportional relationship to the temperature difference compared to the environment. So T infinity is the environmental temperature. We're going to pose this problem, and this is going to be, may seem a little bit strange to you. We're going to pose the problem as being steady. So I say question mark, why? Well, we're going to pose the problem as being steady. We're going to say, okay, look, I've got this slab of material that is 2L in thickness with convective cooling on the exterior of it, and this generation process that is temperature dependent within it. And I understand that as I make this system larger, I expect the temperatures inside to increase. And let's make sure we understand that. So let's even think about a simpler problem. So a simpler problem is this. If you had a constant heat generation, Q dot triple prime 0, between a fluid with heat transfer coefficient H, temperature T infinity, and somebody asks you, what does the temperature distribution look like in this? You should be able to identify what that looks like. And what you're solving is you're solving this equation, K d squared T dx squared is equal to minus Q triple prime 0. So we're solving that. Simple. You just integrate it twice. You get a parabolic distribution. And the wall temperature is such that it has to be high enough such that globally, when you integrate the amount of generation inside there, it has to equal the amount of heat losses out of the system. So what that says is, if I increase the thickness of this, so if I had that system and then I had the exact same amount of generation, the temperatures inside have to increase because the integrated amount of power inside has increased. So I haven't changed the surface area. So to get a steady state, to make sure that I get the heat out of it, the peak temperatures have to be higher. I hope that makes sense. So I want you to think about that that question. So just in the case with a constant heat release rate, the temperatures have to be higher in the slab. Okay? So now we can think about this as, well, what happens if we piece that, so we have that problem in mind, and now we think, well, what if we think about the variable heat release rate problem as a modification to the steady problem? So if I have a constant heat release rate and there is a steady solution, and I increase the extent of that system, I would have higher temperatures because, again, of the points that we discussed. But now, if that heat release rate is temperature dependent in such a way that it increases with temperature, I get a much larger increase in temperature because my rate of energy generation is larger than what it was in the smaller dimension system. Okay, I'm maybe sort of beating an obvious point. To solve this equation, we need two boundary conditions. So the two boundary conditions are a symmetry condition and this Robbins condition, this mixed condition, where we're saying that the heat loss, so this is the heat flux, Q double prime, is equal to what we would get from Newton's law of cooling, this convective heat loss model. Okay, so I'll let you go through this in your notes, but it says that just solving this system, we can render it non-dimensional, and there's some interesting and useful reasons to do that. So what I do is I define a non-dimensional temperature, I define a non-dimensional distance. In terms of these non-dimensional parameters, we have the same equation, just non-dimensionalized. But what we're going to do is we're going to abstract and pull out certain things from it. So what we pull out is we pull out a term, this L over KT infinity, that looks like a conductive loss because KT infinity over L looks like a heat flux. And we pull out a term LBT infinity that looks like a reaction term. And everything else in here is non-dimensional. So what we do is, and this is common in combustion problems, is we talk about the fact that this parameter, this LBT infinity over KT infinity over L, it looks like a reaction rate divided by a loss, a heat loss term. Okay, so think about that. Reaction rate divided by heat loss. If the reaction rate is small compared to the heat loss, nothing's happening. If the reaction rate is large compared to the heat loss, that thing is going to ignite. Okay, so remember that. Think about that. That parameter is called the Damkohler number, and we give it the symbol dA. So dA is the Damkohler number. And here we're looking at it as this delta squared. We made that parameter delta squared. Another way of thinking about it is the time scale for loss divided by the time scale for reaction. So if the time scale for loss is short, it doesn't take very long at all for you to lose the heat. If the time scale for reaction is really long, then it takes forever to get a reaction to happen. Again, nothing happens, okay? So delta is just a number because it's based on characteristic parameters of the system. If we solve this differential equation, again, not a hard differential equation to solve, we get when we solve this, we get a sine and a cosine, and when we apply the boundary conditions, we get t minus t infinity in terms of a constant and the sine and cosine. Remember, we set this problem up as being steady. We understand the thermal runaway is an unsteady process, but, and this is the important part, but this particular solution shows that there are values of delta and this thing called this BI. The BI parameter is called the BO number. And the BO number is H characteristic dimension over K. It's a measure of the conductive resistance to the convective resistance. So it's a heat transfer parameter. And what it says is that if the BO number is small, there is no conductive resistance, and the body is basically at the same temperature, but you can have a large convective resistance. And so a way I like to talk about this parameter is, say you're fixing the inside temperature of a slab at T1, and the outside you have H T infinity. Now, there are a whole range of solutions. So this has some length L and some thermal conductivity K internally. So there are all sorts of different possible temperature profiles internally here relative to what goes on outside. And the important aspect of this is that this surface temperature here, so we can think about it like this, K T1 minus T surface over L is equal to H T surface minus T infinity. Okay, that's just a balance there. And what that balance suggests is that HL over K is equal to T1 minus TS over TS minus T infinity. Okay, all I did was just rearrange that. That HL over K, again, is the BO number. And our interpretation here is, again, that if the BO number is small, it means that there's not a big temperature difference internally. So this is our BO number small case. So here's BO increasing. So BO small is up here. BO large means that the surface temperature is the same as T infinity. So we can, that BO number is just that parameter identifying some of those key features. But we see that the denominator blows up for particular values of that Damkohler number and particular values of the BO number. Where that solution blows up, it means that the solution is no longer valid. It means that we have thermal runaway. And so again, here I'm talking about the BO number in some more detail about what it really means. And we can identify this critical Damkohler number in terms of the BO number where this thing blows up using this simple formula. So this just comes out of modifying what we had before. And so for different values of the BO number, we have different values of this critical Damkohler number. And we see that it depends on the geometry, etc. So if our Damkohler number for our problem is greater than the critical value, there is no steady state, and we have thermal runaway. So we did this problem. And so oftentimes in books, you'll see the Damkohler number, critical Damkohler number for some simple geometries, whether it's a sphere, a cylindrical system, or a slab. And where these have been solved using Arrhenius model kinetics for that Q triple prime term. Okay, I think we're running out of time here. Okay, so that's where we're going to end this particular lecture. We're going to end with this discussion again of spontaneous ignition and what one could do, for example, even with that cotton ball problem, is do some experiments to calibrate what the heat of combustion is, what the activation energy for that system would be, and then identify what the critical Damkohler number looks like for different sizes of that system. All right, we'll end this lecture on that note.